We're going to complete the notes section of chapter 8, dealing with confidence intervals for means. So we've laid down the foundation, then we went ahead and we talked about confidence intervals for proportions, and now we're going to shift gears into means. So again, one of the most important things that you need to be able to do is differentiate between a proportion problem and a mean problem. Once you've been able to differentiate between the two, then it's the same basic process, but obviously knowing the nuances between the differences that we're dealing with. So we're going to look at some activities as we go through in class in this section. There are actually two different confidence intervals for mean problems. For proportions, we only had that one proportion z interval that we've looked at. For mean problems, there are two choices. There's what's called a z interval and then what's called a t interval. The difference between those two things is whether or not we know the population standard deviation, okay, that lowercase sigma. Now, most common, you do not know the population standard deviation sigma. If you were to know that, you would be using what's called a z interval. That's very, very, very rare. So most frequently what we'll be using is a t interval, okay? A t interval is the same concept, except it's using the sample standard deviation. So when do we use a t critical value rather than a z critical value for calculating the confidence interval for a mean? We use a t star value when we're given the sample standard deviation, and the population standard deviation sigma is unknown. This is the most commonly used interval for a mean problem. It's very, very rare that you would know what the standard deviation is for the entire population. If you were to know that, you probably know what the mean is for the entire population as well, and therefore you wouldn't be actually creating a confidence interval to estimate that. In the rare case that you happen to know the population standard deviation, which is extremely rare, aka it's not going to happen, we would be creating a z critical value and creating the z interval. So how do we calculate t star, and how do we calculate the degrees of freedom? So we're actually going to be using that same chart that we were using to get critical values for z. But we have this thing called degrees of freedom, and degrees of freedom are calculated by taking n minus 1, n being your sample size. So when we're dealing with a mean problem, we need to first determine what the degrees of freedom are, and then go to our table, and we need to find the degrees of freedom, and find the critical value, or we can use inverse t on the calculator. So we go to table B, which is what I like to use here. Notice we've been using the infinity row. The infinity row is what's used to get your z critical values. To find your t critical values, you need to go ahead and determine the degrees of freedom, and then go ahead and look at what the confidence level you're using is, and find the corresponding critical value. For example, say we wanted to find the t critical value given a sample size of 25 and 95% confidence. So if my sample size is 25, my degrees of freedom is going to be one less than that. I'd be in the 24 row, this row right here. I'd go to 95% confidence down below, find my way upwards to degrees of freedom in 24, and I get my t critical value of 2.064. Notice the corresponding z critical value is 1.960. What I also want you to notice is as your degrees of freedom increases, aka as your sample size increases, notice how your t critical value ends up approaching the z critical value there. So what is the t distribution? It's very, very similar to a z standard distribution. It's symmetric, it's unimodal, but it's not quite normal, okay? It has fatter tails that allows for more variability from the mean. And we'll take a look at the difference between the t and the z distribution in class. T distribution is also centered at 0. It is considered a standardized score. It has greater distribution than the standard normal curve because it has heavier or fatter tails. We'll look at the next examples in class about finding critical values. Moving on, for our three conditions for a confidence interval problem for means. So remember when we had proportions, we were checking randomness, normality, and independence. We're still checking those three conditions of randomness, normality, and independence. However, we're checking them, and there's some slight differences, mainly with your normality condition, which we would have seen in the past. So that randomness condition, it's either going to be a random sample or random assignment, and we must be specific about whether it's a random sample or random assignment. Our second condition of checking normality, we don't have the large counts conditions or proportions. Remember, now we have the central limit theorem. So our sample size has to be greater than or equal to 30. But go ahead and take a look at the second part of this condition. If your sample size is not greater than or equal to 30, we're hoping our population's normal because then the sampling distribution is automatically normal. But oftentimes that won't be the case, and you'll have to actually graph the sample data, either using a dot plot, a histogram, or a box plot, and comment that there's no obvious skewness or outliers. As long as that sample data doesn't have any major skewness or outliers, you can proceed with the problem. And then your third condition of independence only goes with a random sampling type problem, and that's your idea that the sample size has to be less than 10% of the population size. We had standard error for sample proportions. We have the same idea for your sample means. So in terms of interpreting this value is on the formula sheet. Okay, if we go ahead and we look at our means, one population mean, you see your standard error formula right there. So it's just S, which is your sample standard deviation over the square root of n, and that describes, similar as for proportion problems, how far your X bar will typically vary from mean in repeated random samples of size n. The specific formula sheet for the confidence interval for means is not on the formula is not on the formula sheet, but it's your statistic plus or minus your critical value times the standard error of the statistic. For mean problems, we're looking at an X bar, aka your sample mean, plus or minus, most commonly T star, your critical value, times S, your sample standard deviation over the square root of n. In the extremely rare case that you would know sigma, that T star would become a Z star as your critical value. But here's your formula for the confidence interval for means. So again, just think to yourself, statistic plus or minus critical value times the standard error. This part in here, the T star times the standard error part, that represents our margin of error. We'll look at the next example in class. Final part of the notes that I want to talk about is how can you lose credit for the normal large sample condition on the AP exam? If you're using the central limit theorem, meaning that your sample size is greater than or equal to 30, you want to mention that you're using the central limit theorem and show that comparison. For example, 45 is greater than or equal to 30. If n is not greater than or equal to 30, it's less than 30, you must show the graph and comment that there's no obvious skewness or outliers in that sample data. If you can see that the normal or the large sample condition is not met, you want to make comment about that as to why it's not met, but then you may proceed with caution to continue the problem. Final part here, can you use the calculator for the do step? Yes, you absolutely can use the calculator, but you risk the opportunity for partial credit when you're using the calculator. Similar to when we did stuff with normal CDF, okay? Can you use a calculator to do something like that? Sure, but if you do, there's no real opportunity for partial credit as opposed to finding the z-score and doing it by hand. Same idea here. Can you do it by hand? Can you use the calculator? Absolutely you can. But if you make a mistake, you're not going to get any partial credit. In addition, you must state the interval and always check the conditions, that randomness, normality, and independence condition. Where is it on the calculator? On the calculator, it's under stat, over to tests. Then we've got our two intervals for means, a z and a t. As I said, the z interval you almost will never use, so we're really looking at number 8, which is our t interval. You'll notice that there's two choices here. There's one for data and there's one for stats. Data means that you've actually been given the raw data and you've entered that data in the calculator, as we're going to see in this example in here when we're given raw data. You would use the stats option when you're given the mean and the standard deviation and the sample size, as we are in the example here where they tell us here's what the mean weight is, here's what the standard deviation is, here's the sample size. So you have these two choices as to which one to use when you're talking about a t interval. Data, if you're actually entering the raw data into the calculator, and stats when you're given the sample mean, the sample standard deviation, and the sample size. We'll look at a lot of examples in class. I'll see you then.